Back with another video, and yeah, this is the first part of the exploit development and reverse engineering sort of course, you could call it. I don't know, we're learning it together, so it's kind of confusing. Now we would be referring to the codeland.be site as I stated before, and we'll be starting with the first tutorial, which is stack based overflows. So basically stack buffer overflows. Now I highly suggest that you read this. Most importantly, read the theory part. Things like the registers and the memory pointers and all that stuff, the stack. Even though I explained the stack in my previous video, I highly encourage you to watch that as well. And if all of that is done, I guess we are ready to begin. So the objective here is to overwrite EIP, which is a pointer and a register basically. So EIP will point to a location in memory, so we need to overwrite that with an address that contains our exploit. Now what the tutorial plans here on doing is flooding ESP with our buffer, with our exploit basically. So if this is too confusing, just stop the video and go and have a quick read on this. You'll understand everything, but I'll try my best to explain whatever I can in the simplest words. Anyway, so just to give you a rough idea of what we are planning to do here, I have a working exploit here. So this is what we aim on doing. Now in the tutorial they have used Perl, but I'm gonna be using Python because that's what I'm comfortable with. Anyway, I've just copied this string from Codeland, this one. We're gonna be needing it later, that's why, to test a couple of things. We'll get into that later. Anyway, the string is from Codeland. So I'll be doing this exploit on Wine, using Wine on my Mac, and then when we want to come to the final stages of the exploit testing, I'll load up the VirtualBox. So first we need to find out how much does it take for the application to crash. So what I've done here is I've created a file object, and we are going to be opening a file crash.m3u to write. Now what this application does, the vulnerable application, is converting files to MP3 or MP4. Yeah, MP3, sorry. So we open this for write. Now I don't want to be explaining every single line of code to you guys because I would expect that you have some knowledge in programming. But anyway, so we're going to test how much, so we're going to take A for example, and we're going to test how many A's does it take to crash. So I'm going to start off with 20,000, and yeah, let's save this. This is test.py. I'm going to open up a terminal. It's a new window. We're going to be needing this window. So yeah, let's cd the desktop /codeland exploit writing part 1. We're going to do python test.py. So it prints it out 20,000 A's. We have the file generated in the folder. Now we're going to run the application. As I said before, I'm running it using Wine. We'll load the VirtualBox up later because it uses more RAM, so I don't want to have any lag here and there. Anyway, let's run the application. It takes a while in Wine usually. I don't know, how do I just leave some tips down in the description. I want to increase the speed. Okay, it finally opened up. So yeah, now we're gonna load our vulnerable file in this. Let's just ignore this stuff. So let's load our crash.m3u, all files, crash.m3u. So we haven't crashed it. The exception is handled correctly, but our objective is to crash. So I'm gonna increase the number of A's by about 30,000 more. So by 10,000 more, sorry. So we have 30,000 A's. Let's generate the file. Now let's try it in our application. So let's load again. This should crash, and yes, we have it crashed. So it takes about 30,000 30,000 of random shit to crash the program. Okay, so now once we know this, we are gonna need to fingerprint more. One sec, just quit this stuff because it's not responding. Well, yeah, anyway, so we know that it takes 30,000 or whatever to crash this program. Now we need to see where exactly, now exactly to place our buffer and our stuff like that. So let's refer to the tutorial. I'm going to skip through the theory, but I'll explain whatever I know as we go on with the exploit, because this would take a lot of time. Anyway, now what they do here is, so this is all the stuff in hex. So 41 is A, 42 is B. Anyway, now they have created two junk objects. So one would be 25,000 A's and the second would be 25,000 B's. Now the objective here is to see what EIP is overwritten by. So they are trying to determine where EIP sits between. So how much does it take to reach EIP exactly? Now let's just follow all the test stuff here. So we're going to do 25,000 A's and 5,000 B's like this say, and I'm going to open the debugger and show you. So chunk is equal to 25,000 A's and chunk 2 is equal to 5,000 B's. Sorry, 5,000. Now that will make it 30,000 because we know that it requires 30,000 to crash. So string is chunk plus chunk 2. We're going to print the length of string, f.write string. Okay, anyway, let's run this. Python test.py 30,000. I'm going to open the debugger up just so we know, we get a good idea of what works. I'm going to just clear. I'm going to open the program in the debugger itself. Okay, so this is immunity debugger. So this is where the instructions are. This is the hex dump. These are the registers, and this is the stack. This is, sorry, wait, this is the stack, and yeah, no, wait, sorry, yeah, this is the stack. I'm sorry. Anyway, let's open our vulnerable application in immunity. Like I said in my previous video, you can use any debugger you want. I'm just comfortable with immunity, so well, that takes a while. Okay, so these are the instructions and this is the stack. Now I'm just gonna enlarge this for now. Okay, so let's run our program and let's load our vulnerable application, see what goes on. Now this is EIP. As I explained before, this is a pointer to a memory location on the stack. We need to point it to ESP. We plan on filling ESP with our exploits. EIP is simply a pointer. Anyway, let's load this file and let's see what happens. So you remember the bees, the bees we filled it with. So now EIP is filled with the bees. Now we know that, just give me a second, let me find the A's here, and that way I could give you a better idea. So these are our A's and then the B's. So now we need to so now we know that to get to EIP we need to manipulate our way into those 5,000 junk. So we need to do something about those 5,000 junk. Now that's why we have something called pattern creator in Metasploit. So we're going to use that. I'm going to just restart this because, well, can't work on a crash program. That restart. Till then, I'm going to need this for now. Anyway, we're going to keep this running in the background. Now, let's go back to the tutorial. They haven't used pattern creator, but still. So as they said, yeah, EIP is filled with the bees. Now, we will generate our pattern from this. So I'm going to open up Now for some reason Mac does not allow you to use pattern creator from the terminal directly. I'm gonna have to go into MSF console and do it. But on your Linux machine, you can do that. You can just run pattern creator from your terminal. I'm gonna have to go into MSF console and do it. So now we are going to be replacing the B's for our pattern creator. So just remember that the pattern that gets created will be of length 5000, and we'll replace that with chunk 2, with the B's in chunk 2. Now I'll tell you what this does after a pattern is created. You know, this stuff will seem really clear to you once you have enough practice and enough understanding in the topic. I mean, it took me a while to figure out Exploit Tutorial 1 alone, and I have a second way of doing this too. We'll get into all of that later. So let's go into, this is the directory for Mac, just remember that. And for Linux, it's in user share Metasploit framework, and you'll find the tools there, /tools obviously. Anyway, now we're gonna run pattern create.rb. Tag L for length of 5000. Is that 5000? Yeah, that's 5000. Now always remember that exploit dev requires a lot of calculations, and you cannot go wrong in your calculations. Now I'm not saying take a paper and do that stuff. I mean, you can do it in programming languages, but the point is that this will work only for this Wine environment. The calculations I'm doing now will only work for this Wine environment. So if you have to perform this on another machine, you're gonna have to do this pattern thing all over again to find the offset. But there are other ways of developing versatile exploits, and we'll get into that in the next tutorial. So anyway, we are gonna place our pattern here, a really long pattern. Anyway, command save. Now I'm gonna keep this open because we're gonna need to find the offset. I'll explain what an offset is later. So cd desktop /corlan okay, Python test.py 30,000. So let's redo the immunity procedure. Let's load the program up. Load. Yeah, that's it. All files crash. Open. Okay, now just pay attention here for a second. Now this is ESP. Can you see this address here? 0030 EAA8. This is this address, ESP, right? You can see that's the same. Now we need EIP. I need to find out how much do I need to overflow by to reach EIP, and then we can fill EIP with an address. So EIP is here, 0030 EAA0. So if you convert this value into that's it. Yeah, this is the one, 306A4239. 306A4239. Now this is those 4 characters that ended up in EIP. So what I'm gonna have to do is I'm gonna fill random stuff till here, and in EIP I'll get to, our objective is to control EIP and ESP. So first let's focus on controlling EIP, so we can place whatever we want in here. So we are gonna have to overflow till here. So now the characters here are 9BJ0. It will be different for you. Now just keep this in mind because we're gonna need this. I'm gonna minimize this for the moment. And now I'm gonna find the pattern offset, which means that one sec, I'll just unload this, restart this. Always keep restarting the program in your immunity, or you'll be working on some weird stuff. Just keep restarting it. Anyway, let that get done. Okay, this is our MSF window. Okay, what happened here? Okay, whatever. Anyway, now we're going to find the pattern offset, which again means that we're going to find how many characters does it take for it to reach there. Okay, well, I forgot the thing. Yeah, okay. So, yeah, so it is 9BJ0 at EIP. So what we're gonna do is we're gonna find the pattern offset till there. So I'm gonna do Ruby. It's in the same directory as pattern create. Pattern offset dot rb. Tag q means query for those characters. We are going to find where in the pattern and how much did it take to reach here. 9bj0. Q 9bj0. Remember these characters. These are extremely important. If you mess up here, you mess up in your calculations to EIP. So let's query this. By the way, the editor I'm using is Atom, really beautiful looking thing. Anyway, this is the offset. Now, in our pattern, till 1049, after 1049, 1050 is EIP. So what we're going to need to do is, I'm going to note this down, because this is extremely important. Now keep noting down what you find in your debuggers and stuff in your exploit code, because it helps you understand what you were doing at that time. Now what we're going to do here is we're going to fill the A's with 25,000 plus this much till we reach EIP, correct? So I'm going to do A of 25,000 plus 1049. And in junk 2, I'm going to do a little magic. I'm going to see if we go correct in our calculation. So I'm going to fill it with 4 B's, because 4 is basically the amount that needs to be in one register at the time. So 4 B's. Now if everything goes correct, I should have 4 B's sitting lying around in EIP. So let's see that. We're going to exit out of this. I can shut one terminal window, so well, you can go. We'll exit out of this because we don't need this at the moment. We're going to generate our thing again. Oh wait. The calculations went wrong, because it's supposed to be 30,000. Just give me a sec. Let me refer to my working exploit. So I did the same thing here. Oh yeah, wait a second. Oh yes, so now string is gonna be now I'm gonna put another junk variable, just so that it's sort of a sanity check that we are doing 30,000. So I'm gonna put junk 3 is equal to, say, C's. That will be, oh yeah, C's of length 30,000 minus junk, yeah, the 30,000 minus junk plus that. Just give me a sec. Do length of, wait, yeah, one sec. Shit, what is wrong with me? Anyway, yeah, sorry. So 30,000 minus length of junk plus junk 2, right? So it will be those many C's. I'm just gonna double quote these, and junk plus junk 2 plus junk 3, right? Junk 3. Now, actually, wait. I'm gonna name this. Okay, never mind. Just let's keep that for the time being. I'm gonna save this. That's why I said the calculations are extremely important. So if everything goes fine, we should get 30,000. This is extremely important. This serves as a sanity check. Anyway, I'm gonna reload this stuff. So restart. Now, if everything goes fine, we should have 4 Bs in EIP. That's something we need to remember. So let this load up. Yeah. So let's start the program. Let's load our file. And 3U crash. Yeah. And well, our calculations did work. So our EIP is filled with the four B's we put in, and ESP is filled with the C's. So now I know that the ESPs are going to be filled with the C's. So I'm going to name junk 3 as ESP just to make things easier. I'm going to restart this for now. So our calculations are correct. Now we have control over EIP. That's something we need to know. Now I'm going to change this to ESP because these are the contents of ESP, right? So junk to ESP, right? Now we know that this is where our EIP stuff goes. So I'm going to also name this as EIP just so that we know what's what, and junk will remain as junk. I mean, junk is junk, so it doesn't matter. Junk plus EIP and junk plus EIP plus ESP. Okay, so now we have control over EIP. Now let's go back to the tutorial and see. There's a bunch of stuff. They have also put C's here. This is okay. Now we need to find the memory to host our shellcode. So now they have taken obviously almost the same things that we have, and A is our junk is that, and EIP is the 4 B's. And now in ESP we are gonna put this string. Remember this one that I copied? Yeah, we're gonna put that. So I'm gonna rename ESP as shellcode just so that we don't get too confused. Or buff. Yeah, let's name it as buff. You'll know why later. I'm gonna just erase this string then. It makes no sense to keep it. So I'm gonna copy this. Command C, Command V. Uncomment this. And I'm gonna do EIP plus buff. Buff. Now this is also the same thing as the pattern, just that we need to know that all of this goes in ESP. We need to know that none of this this pattern gets overwritten by something. So I'm gonna save this. Yeah, let's just check. Yeah, everything seems to be fine. Now we should get about what, 30,000? Or wait, no, the calculations are long. Yeah, just give me a sec. I'll put more stuff. Yeah, I'll put just a junk 2 just as the C's, right? So C's of, yeah, I did a mistake erasing that. 30,000 minus length of junk plus EIP plus buff. Yeah, that works. Anyway, and is this stuff done? Junk plus EIP plus buff plus junk 2. Wait though. Yeah, plus junk 2. I'd like it to be in this order. Just matters to a certain point. Yeah, anyway, let's do that. We should get 30,000 just as a sanity check. I'd like to keep it as 30,000. Anyway, where's debugger? Yeah, debugger. Now we're gonna load our thing again. Where is the thing? Yeah, run. Load. Oh, come on. Load all files. Crash. Now this is something to note. This is ESP, correct? EAA 8. Now four characters of our pattern did not go in ESP. This can create a problem for us because we need all of our pattern to go. This is 144 bytes long total, combining the 1A PC. Now if I add 4 bytes before this, you know that the whole thing will come in, right? Yeah, simple math. So what I'm gonna do is I'm gonna name something as, I'm gonna create a variable called pre-ESP. I'm gonna fill them with a bunch of x's. Shit. Bunch of x's. 4 x's to be precise. And that could be that, and we need to add it in here as well. Plus pre-ESP plus buff. We are gaining control over the register ESP. Now let's generate that. Oh wait, calculation error. 29. Oh, that's odd. Let's see, what didn't we add in here? So junk, EIP, pre-ESP, buff. Oh yeah, obviously we didn't do this. So that's why I print the length of the string out, so that I know that I'm not making any mistakes. 1 2 pre-ESP plus buff plus jump 2. Yeah, now this should work. So these little small improvisations in your code can really help you in the long run. So let's load our thing here again. Come on, let's go. Yeah, let's run it. Okay, load and that file again, and voila, we have our whole thing fitting into ESP, and our pre-ESP is filled with the X's. So now we have gained control over EIP and ESP, which is a good thing. Now this is where our shellcode is going to be. This is our shellcode. This 1AVC crap is our shellcode. All of this is 144 bytes long. We know that we have this much space and nothing is going to get overwritten. Now this is our pre-ESP, just to make sure everything goes into ESP and EIP. Now we need to fill this up with an address that jumps to this. We need an instruction that jumps to ESP. So now you must read on instructions in assembly line. It's there in the Codeland website. Now what jump means is that if I override this with a thing here, an instruction that contains jump ESP, it will jump to our shellcode. That's our objective. I'm going to restart this. I'm going to look for that instruction now. Now there are two ways of doing this. So one is obviously finding the jump ESP instruction, and second is to find a push plus return instruction, both of which will work. So first let's do the first one. I'm gonna make sure your program is running, and now we'll do nothing. We are gonna search in all executable modules. We're gonna search for all commands in all modules for jump ESP, JMP ESP. Okay, now look, we have a jump ESP right here in the DLL of this thing, the application MSRM codec 2. This belongs to our application. So let's go here. I'm going to copy this. Now this FFE4 is actually the opcode for jump ESP, the instruction. So I'm gonna copy to clipboard. We're gonna paste this in our code for later reference, right? So command V. Now I'm gonna import a module here, import struct. Now what this is gonna do, now you need to read on one more thing. Endin formats, little endin and big endin. Now we need to send this address into little endin format. So that's why I'm gonna use struct. This is our thing, right? So wait, let me just reload this to make sure nothing's running. Anyway, now we have this instruction which is jump ESP. This will jump to our shellcode. We need to place this address in EIP. So EIP, in EIP we are going to do struct dot pack. I think that's the one, yeah. You need to also read on how this function works. I'm just going to refer back. Yeah. So now what this means is when I do this sign an I, capital I, it means an unsigned integer. That's what we need to convert to little endian, and our address here with a 0x in it. What we need to put into EIP to jump to our shellcode here. Now I'm also gonna do a couple of more things and buff. I think we can move on with the exploit. Or no, actually, let's just do this for now. So in my previous working exploit I did this, and now yeah, I'm gonna also include a few of pre shellcode thingies. Basically all the okay, yeah. First let's test this. Command save. Let's see if it jumps to our buffer here. So yeah, 30,000. Now let's load this and let's see if it jumps to our code. So yeah, wait. It should jump to our shell code if everything works fine and if the address works. So I'm gonna load all files, crash.m3. Yep. So it jumped to our shell code. See, this is one of those characters. I mean, it will jump, yeah. So it jumps to ESP basically. That's what we need to know. It jumps to our shellcode. Now, why it doesn't completely jump to the starting of the shellcode is because we don't have something called nops. Now, nops serves like a kind of buffer for our shellcode, which allows it to overwrite itself basically. It's like a buffer, as I said. So I'm gonna restart this. Basically it works, it jumps to ESP. We just need to include our thing in ESP. So now what I'm gonna do is I'm gonna shut Wine off. I'm not gonna use Wine. I'm gonna boot up the Windows VM and we are gonna do it there, because then you can see the exploit working. It will open a calculator. I've loaded my Windows XP Service Pack 3 machine, and I had to change a few calculations and the memory location here, because as I said in the last video, your exploit will only work on the machine you are testing it on. So every exploit is different in its way and needs to have different offsets and different memory locations, but don't mind that. You keep yours the same because your victim machine is going to be the same. Anyway, this was where we left off. We assumed control of EIP and ESP. Now what's left for us to do is to put our actual shell code in here. Now what I'm going to generate is going to be a calculator payload, which is every hacker should know that it's used to generate payloads. Tag p windows/exec, which stands for executing commands, and the command is equal to calc. So if you go into command prompt and you type calc, it usually opens up the calculator. So calc opens up the calculator. That's what we need to execute. And yeah, so command is equal to calc. Tag platform is equal to Windows. Tag A is equal to x86, which is the architecture. Tag F is pi. We are creating the payload for a Python file. And the encoder we'll be using is x86 alpha upper. It's written in the tutorial as well with what encoder you have to use. So I'm going to generate this. As I said before, all of your payloads need to be in hex, otherwise it won't understand it. So it's going to generate all of this in hex. One sec, let's just see. Yeah. Wait a second, I made a mistake here. Okay, anyway. Yeah. So this is our thing. So it's generated it for a Python a file for a Python exploit, so we could just copy and paste this in. So I'm gonna erase this whole line and paste it in. This is our exploit. Now one thing we also noticed in the last part was that the string, when we did jump ESP, it wasn't starting exactly for one ABCD because we did not have a buffer, so it was running out of space. So what I'm going to do is create a variable called pre-shellcode, and that is going to consist of something called NOPs, non-operators, which does not execute anything basically, but it will serve as a buffer for our payload so that it can overwrite itself. It gets a little bit of head space. So I'm going to put that in ASCII 90. The character is ASCII 90, x 90 5. Come on, save. Yeah, we forgot to add the knobs in, so that's the mistake. Now I'm gonna shut that in, and yep, let's run this. Now it should work. 30,000. There's the thing. Yeah, that's it. Dash M3U. Yes. How it should work. Load. And crash. Well, the calculator. So this concludes our tutorial part 1 basically of Stack Buffer Overflows. Now I'm not saying that you launched a calculator and you're a huge hacker. No. Now I'm giving you guys a task. I want you to incorporate a reverse a bind or a reverse shell, say a bind shell payload into this exploit. I'll be now take a note of all of this, follow the tutorial solid, and then I want you guys to try creating a bind shell, and I want you guys to connect to the victim machine. That's the task for you guys. So tell me in the description how did things work out for you guys, and I hope you enjoyed this tutorial. Please make sure to like and share, and also subscribe if you can. And yeah, it won't be long. I won't take too much time to release the next video. Okay, anyway, see you guys. Bye bye.